Good morning, physics. Today is April 30th, Thursday. Today we're going to be talking about modeling waves, which is the next section in our ebook. Yesterday and the day before, we were talking about classifying waves. So we talked about the two major types of waveforms that we have, which are transverse waves, which are like the ocean, where it goes up and down. And then we have longitudinal waves, which are compression waves, and sort of how sound gets from, say, my voice to my microphone and then from your speakers to your ears. And with this, we're still sort of on the topic of mechanical waves, which means waves going through a particular medium, something like air, water, all of that. And we talked a little bit about sort of some of the components of the wave, like the wavelength and the frequency. But what we're going to be doing today is sort of going deeper into the components of our waves. In fact, we're going to sort of, for what you're going to do tomorrow as sort of an at-home activity, you're going to create a model of a wave and label it. So with this, what we're going to be doing is, so we're modeling waves. And one of the biggest things we can do is sort of with sound, and sort of how all of these components of our wavelength are created. So to start us off, we have, normally what we do is if we think about the water that you had yesterday, I probably should have done that in blue. Oh. So we had the water that we had yesterday, just like that. Sort of that was the surface of it, and now what you did is when you dropped some water on it, what ended up happening is we ended up sort of getting our waveform, which looked something like this. And when this happened, we have a few different components. So if I drew smoother, this would be our peak. So we have a peak. We have our troughs. And then one of the key things we have is if we were to measure. So we talked about wavelength previously a little bit. But in terms of like what wavelength is, wavelength would be the distance from here to here. Similarly, wavelength is a little bit related to what is called the period, which is sort of the inverse of the frequency. So if we wanted to find the period, like say this was a wave moving through the water, what would happen is the period would be the amount of time it takes for the wave to complete one wavelength. So if this wave from the water droplet was moving this direction, the period, so the amount of time it takes for it to sort of complete a wavelength, would be the time it takes for this wave to get all the way over to here. So like it would be the distance from the time it takes for one peak to get into the same position as a previous peak. So it'd be like one full thing. So it would take however much time it takes for this peak to reach all the way over here, because since these functions, these waves end up repeating themselves over and over again, that's sort of one way we've determined how to measure these things. And with this, those are sort of important components of it. But one of the other things is if we notice what should be happening here, I didn't quite draw it to scale, but the amount of height the peak should be equivalent to the amount of depth the trough is from the sort of water line. So what I'll do is I'll label it. So this should be, I'm going to just say same distance. Although my S and my same Did not quite come out right. It's like game distance, same distance, which that is basically labeled as the amplitude. Which we'll talk more about amplitude, but the idea of amplitude, it's sort of the distance from the undisturbed portion to the either peak or the trough. Or if you think about it, it's half the distance between a peak and a trough is the wavelength of how these waves are formed. You'll learn a lot more about these types of waves and sort of periodic functions when you get to pre-calculus, because these can actually be expressed mathematically, and as you go further on in math, eventually with, say, things like what are called Fourier series, you can actually model sounds using a whole bunch of different waves, which is really cool and pretty complicated. So, with that, in order to get to the section today for what you need to read, let me pull it up. Oh, wrong one. So, you log in, you get here, you click on Waves, it'll pop up your ebook, and then you'll click on Contents and go to Lesson 1, Waves and Matter, click the arrow, and Explore Explain 2. And then you can click this if you don't want the contents over there. So within this, we're going to be talking about a few things. You're going to be reading about sound in depth, and sort of with this, it's sort of how waves of air sort of travel through. If you look here, there's all of these dots. These dots represent air molecules. So if you play a sound, what's actually happening is you're sort of creating waves within the air molecules, places where the air molecules are sort of more densely packed, and where they're less densely packed, causing vibrations. And a lot of that is so one of the things you read about Tuesday was sort of the idea of thunderstorms, and how as temperature increases, the speed of sound increases because they have more energy. Another sort of thing that happens is it sort of becomes a little bit less compressible. When you have higher temperature airs, it wants to fill up a bigger volume. You can have a pressure increase. And that's sort of one of similar reasons why sound travels a lot faster in water and ends up having a higher pitch, is because it's able to sort of make those collisions a lot faster in water than it is in air, because everything is much closer together. So as you go here, there are some components of it, and one of the things I'd like us to do, so you can sort of do some things to sort of, if you think back to Explore Explain 1, you actually have the equation here for this explain, where you talk about speed is something times something. I'll give you a hint, it's times something else. And then if you're really confused, you can actually go down here to figure it out. So what I would like to do is actually go through this sample problem, because there are a couple more. There's about 4 more problems you're going to do using the V equals lambda F, which is velocity equals wavelength times frequency, and you're going to rearrange that equation, and you're going to solve some problems. So let me go ahead and pull up the whiteboard, and let me get this sort of showing. All right. So with our sample problem, let me roll down. So with our sample problem, we have 2 things going on. A little bit squeezier. So we have a piano string tuned to middle C, vibrates with a frequency of 262 hertz. Assuming the speed of sound in air is 343 meters per second, which that's usually at room temperature, is the speed of sound in air, 343 meters per second. Also the how fast a jet needs to travel in order to break the sound barrier or start breaking the sound barrier. It needs to be going at least 343 meters per second. So with this, what we're going to do is we're going to write it out. So let's first write out our equation that we're going to use, which is V equals lambda F. And then let's go ahead and let's start sort of filling in the information that we do know. So with it, we do know it gives us our frequency. So F equals 262 hertz. Now, hertz is sort of an interesting unit. It just sort of means cycles per second. So if you think about it, so cycles per second is really weird as sort of an idea, but it basically works as sort of, if you think about it like you're on a bicycle, and every time, each cycle would be one moment where you sort of have your pedals go all the way around in a circle. That would be one cycle for you. And so the number of cycles you do per second would be your frequency. So you could end up biking at a frequency of, say, maybe 10 hertz if you're going wicked fast. That might be a little unreasonable. To be honest, I'm not actually really sure what a reasonable frequency is for spinning your pedals as cycling. I've never really thought about it, but if someone, as part of their daily get out of the house and do something, decides to measure their number of cycles they have while biking, I would be interested in knowing what you calculate or what you find. So, 262 hertz. And then if we know our velocity, so we can say V equals 343 meters per second. And then last but not least, what we're trying to find is our lambda. So lambda equals, we're sort of going to use our equation. I'm a little bit ahead of us. Sorry. So first thing we want to do is rearrange this equation so we can do it. If we think of everything as things we can divide by or multiply by, it makes it a lot easier. So when we start from here, if we're trying to solve for lambda, so what we can do is divide by f. So if we divide by f, we end up with lambda, that was not supposed to be a triangle, lambda equals v over f. So now when we plug in our numbers, we get lambda equals 343 divided by 262. And then we plug it into our calculator, or in my case, I just scroll down and do a little cheating. We get lambda equals 1. Let me actually just scroll down and put it in a better position. We do the math, lambda equals 1.31 meters. So basically, in these problems, you're going to have to rearrange your equation, which is v equals lambda f. There are three forms of it, which I'll just write right now to make it easier. We have our original form, v equals lambda f. And then we have our solve for lambda, which is our wavelength, equals v over f. And then lastly, but not least, we have our frequency form. So if we're trying to find what pitch a note is, we could have f equals v over lambda. So these are our three forms of our equation, and that's the idea for today. Tomorrow, what I'm going to have you all do is you're going to create a model of a wave similar to the drawing I did up here, except it's going to be out of things you can find in your house. So rather than drawing one, I want you to make one and label it. Ideas could be a towel. You could use shoelaces. You could use shoes if you have enough of those in your household. But I want you to make a model of a wave and sort of label the various components of it. more points to the more interesting ideas you come up with. I'm just interested. I figured it might be a fun thing to do that will be a little bit creative and also pretty entertaining. And I will share out the best one on the Discord server that I receive, or the one I like most, or maybe we can even have a vote on them. Lots of options here. I just want to try something a little bit different and weird and fun. So that is what's going on for today. I hope you find this useful. I'm sorry it's a little bit longer than the normal videos. But if you have any questions, message me on Jupiter, drop a message in the Discord, or something else.